Hi, welcome to another video on know the basics of circuits. In this video, we will have a understanding of electromagnetic relays. So we'll study SPDT relays, that is single pole double throw relays. Okay, you should be knowing Ohm's law, KVL, KCL for understanding this. And of course, these are the prerequisites. Okay, now we shall proceed with of course, this is the symbol of electromagnetic single pole double throw relay. So this is how that SPDT is coined from, single pole double throw. So we are referring to this as single pole, and we are referring to this being thrown from this end to this end. So this is what is double throw. So this will be thrown from this to this, or it will be over here. So now the question is, when does this common terminal will be here, and when does this common terminal goes there? Of course, since you can see this electromagnetic SPDT relay will have 5 terminals. Suppose you name them as 1, 2, 3, this is 4 and 5. So if you have a look at this relay, so the extreme two wires will be the relay, this is 1 and 2, and this will be the common terminal, and you're going to have two more terminals here. So one will be NC, other will be NO. So what is this NC stands for? This is normally closed. So common and this terminal will be connected under normal condition. So normal condition is one where no current is flowing through this. That is the normal condition. So under normal condition, this common terminal is connected to this terminal, which is named as normally closed. Naturally, the other terminal will be not connected to common, so that is called as normally open, NO, under normal condition of no current flow to the coil. When sufficient current flows through the coil, then naturally this common terminal will be shifted to this terminal, which will be now shorted. So normally open will be get connected to common when sufficient current flows. So I should be non-zero, and it should be sufficient enough so that this can be pulled to this normally open condition. So that's what is a SPDT relay. So let me show you how does a SPDT relay will look like. This is how a SPDT relay will look like, and if you can see here, it has got 3 terminals on one side. Can you see this is 1, 2, 3 terminals, and on the other side you have 2 terminals, and here this black and white are the terminals corresponding to coil. This is the common terminal. So out of this, one will be normally open, other will be normally closed. To make out which is normally open or normally closed, we can actually see the continuity between these two. So what I'll do is, let me show you how to know the continuity. I'm using a multimeter. I'll put it to resistance and then into the buzzer sound. Okay, let me just connect between this common. So this is my common terminal. If I connect it to one of them, you can see this is not buzzer. Okay, this is, can you see the buzzer sound? So now these two terminals are connected because there is no current is flowing. So this is the red one. Red terminal is now called as normally closed, whereas if you can see, this is now open. This is now open. You can see there is no connection between this yellow and the green one. So this is normally open, whereas this is normally closed. Can you see now you are getting a buzzer sound? So buzzer sound means okay, it's a zero resistance. So these two are connected. So that's how we can identify normally open and normally closed with respect to common. So this is how a relay looks like, and this is how uh, inside relay looks like. So this is the cover has been taken out, and this is how it is looking. Okay, you can see here. This is okay, I can show you this. Okay, I can remove this cover further. So I'm just taking out this. See now, this is coil terminal. This is the other coil terminal. They are actually going to this coil wire here. So this is going to coil. Can you see this is a coil here? Can you see there is a coil which is wound, and this is common terminal. Can you see this yellow one is connected to this? So this is common. So here, if you can carefully notice, and of course I'll show you the other picture. So there is there is a middle terminal. So that middle terminal is always pulled up. It's always pulled up, and when current flows, that will be pulled down. So that will be pulled down. So that's what is. So it's of course it's usually up. It will be pulled down when it is when sufficient current flows through the coil. So I will show you images of that. Okay, let me show you. This is how a relay looks like at the top. So this will operate with a DC voltage of 5 volt. The SPDT relays will be of either 2 volts, sorry, either of a 5 volt rating or 12 volt rating. So these are the ratings, the voltage rating of the SPDT relay, meaning I have to connect 5 volt across the coil, and there should be sufficient current flowing through that, so that this common terminal can be okay going to, that will be thrown to normally open thing. So this will be either a 5 volt or 12 volt. That's what is this. I have shown you this is what is that, and you can see this is when it is open. So of course this can handle this much okay AC current, and so this is corresponding to AC rating, this is corresponding to DC ratings. So it can handle very good amount of current as well as the voltage, meaning these copper wires whatever you have here. So this is the terminals. You can see this is one, this and this. You can see on one side you have two terminals, on the other side you have three terminals. So wherever you have three terminals, so this end and this end, the extremes are the coil, the middle one is common. So out of these two, one is, if it is normally closed, that will be normally open. So how to make out? You can use a multimeter to check out. So if common and one of these terminal is connected, whichever terminal is connected with zero current, that is called as NC. Let us go to this. Now you can see this is, I was just showing you. This is if you can see, this is the top terminal. This is that common. Since under normal condition, this is always okay held to this. When current flows, this will be pulled down. This will be pulled down. So this is naturally normally closed, that is this terminal, and this terminal is normally open. This terminal is normally open, and this is the coil, and you can see this is the common. So coil has got two terminals. You can see this is one end of the coil. Uh, this is common terminal. See this is how it looks. This is the other end of the coil. See this is the common terminal. You can see this is one end. This is because you can see there are three terminals on one side. This is one terminal. This is common terminal. This is the other coil terminal. You can see this is the coil wire which is running from this end all the way turned there onto the core, and then it's coming out here. So these are the two ends of the coil. This is practically or a relay module. We'll just talk about that later. So this is the relay. To understand the operation of this, so I have connected a circuit here. This is the connection that is made. So there is a relay of 5 volt rating being used. So I'm using a okay, let me show you that over here. So Okay, this is that power supply that I'm referring to. So this is a circuit diagram that is being connected over here, and you can see this is that 5-volt power supply. And to know the current, I'm having a milliammeter connected in series with the circuit. If I just refer to this circuit diagram, so I have a milliammeter here which is going from plus to minus. This is an ammeter, and it's going to coil. See here, this is the power supply. There is a milliammeter, and I'm using the coil here, and this is a DRB to vary the resistance so that I can control the current flowing through the coil. And there is a switch also. So now let me just try to so now the switch is open. When the switch is open, there is no current flowing through this, and we have actually the NC is now connected to common. So what I have now is I have connected a buzzer here. You can see this is a buzzer of 5 volt. If 5 volt is connected to this buzzer will make sound. So now under normal condition, when no current is flowing, can you see this 5 volt is connected to this 5 volt is connected to NO, and this common is connected to one end of the buzzer, the other end is connected to ground. So actually now nothing is connected to of course no current is flowing through the buzzer, so buzzer is quiet. So now when no current is flowing through the coil, when no current is flowing through the coil, so now this common and NC are shorted, so buzzer is quiet now. When current flows through the coil, this common will be connected to NO, so then current flows through this. Okay, so now whenever sufficient current flows, so you can see this will be connected, so this will be connected here, then current flows from here down from this to the ground. So let me show you that. So I have not introduced any resistance here. Let me make the resistance 0 here. So all the DRB values are 0. The moment I switch on that, you can see, are you getting the buzzer sound? Can you see 66 milliamperes of current is flowing? And can you see this is, of course, you can just carefully notice that what happens to this one. I hope you can able to visualize that. Just have a look at that. Just a minute. Some wire might have taken out. Okay, this came out. Let me just connect it. Okay, now just carefully note. Can you make out that? Just have a look at this point. When I press the button, that actually goes down. Can you see it's going down? Can you see if I release it went up? When it is going up means okay, common is now connected to normally closed terminal. Whenever I push, it is pulled up. Can you make out that? So now when sufficient current flows, you are having common is now connected to NO, so that's why buzzer is buzzing. So now let me reduce the current and see how much is the current that is required to flow through the coil, so that it just pulls down the common lever to NO. So what I'll do is I will bypass this switch. And then you can see, since the current flowing is around 66 milliamperes, it is keep buzzing. So let me introduce the resistance here. So when I'm increasing the resistance, you can see current is reducing. So with 56 milliamperes also, it is that the common is pulled down to NO. You can see I'm increasing. Now it is 20 ohm in series with that coil. It is 30 ohm in series with the coil. You can see it is 20 plus 10. Now I'm having 40 ohms connected. The current flowing through is 42 milliampere. Now it is 39 milliamperes is the current flowing. So it is now pulling 36 milliamperes. Oh, now it has stopped. When the current is 33 milliampere, it is not enough to pull this lever down. So meaning here we said if the current is sufficient enough, then only it will going to make this common will go to NO. So certainly some current is flowing through the coil, but that current is not sufficient to pull this common terminal down to the NO terminal. That's why you can see if I reduce the resistance, the current will increase. The moment I reduce the, you can see I'll reduce the resistance. Can you see the current flows and then sufficient current is flowing. Now the common is now connected to NO. If I increase the resistance, you can see now when the current is around 31 milliampere, it is not enough to pull your common terminal to NO. You can see this is also not enough. It should be more than 34 milliamperes. Can you see it is around 36, 35. It is now pulling it. Common is pulled to NO. Fine. So what the conclusion? Conclusion here is okay. So what the conclusion? Conclusion here is the current I coil. Okay, let me write it here. I coil should be approximately 35 milliampere so that NO and common are shorted. NO and common are shorted. You can see 31 milliampere is not sufficient. It's not connected. 33 is also not sufficient. You can see 36 point something it is connected. So this is the way how we have to understand. There is a minimum current of 35 milliamperes and above that should flow through the coil so that it will make a contact. The common is now connected to NO. If you reduce the current by increasing the resistance, you can see it's open. So now where is common now? Common is now connected to NC. You can carefully look at that. Just have a look at this. Can you see it as pulled down? I hope you are making it out. That is pulled down if the current is sufficient. If I increase the resistance, it goes up. Hope you are making it out. Can you see it as pulled down? Just carefully observe this small deflection there. If the current is increased, it is pulled down. Sorry, yeah. So I'll reduce the current. Can you see it as pulled down? Now the current is 36 milliampere. I have reduced the resistance. It is enough. It has pulled down. I will increase the resistance. Current reduced so that it went up. It came down. This is how a relay operates. The summary is the current through the coil should be approximately 35 milliampere so that NO is connected to common. If I coil is less than 35 milliampere, then common is connected to normally closed. Correct? When it is less than 35 milliamperes, it is basically you need to have a current of more than 35 milliamperes in the design to ensure that much current should flow through the coil so that common is connected to NO. See here 33.9 is not sufficient, that's why it's not buzzing. I'll reduce the resistance, it's fine. Anything more than that, it is fine, but anything less than that, it's off. Can you see it's off, off, off? That's it. Thank you.